No need to copy the questions. You just clearly write down the problem numbers and you write down the solutions only. Okay. All right. So last time what we did is uniqueness and existence of the prime factorization. To summarize, the existence of the prime factorization is proved by the strong induction. You can see the notes that I've been using the strong induction here. And to prove the uniqueness of the prime factorization, we had several preparation to them. One of them is Euclidean division algorithm, which is the existence and uniqueness of the quotient and the remainder when we divide by non-zero integer. And you can see that several times we are using the well-ordering principle. The well-ordering principle states that any non-empty subset of natural numbers has the least element, the smallest element. And we have a divisibility definition. And divisibility is transitive. And also the greatest common divisor, GCD. Okay, we prove the existence by using the well-ordering principle. And we have a strengthened version of the existence of GCD, which is namely Badge's lemma. And the Badge's lemma can be summarized as AZ plus BZ, the sum of the multiples of A and multiples of B, that as a set equals to the multiples of GCD of A and B. Okay, again, well-ordering principle is used, right? And once we are done with the Badge's lemma and the remaining preparation for the uniqueness of prime factorization includes if the integers are relatively prime, then one is a linear combination. If a prime is not dividing an integer a, then the GCD of a and p is 1. And if the prime divides product, then the prime divides the first one or the latter one, and can be generalized to many integers multiplied. If a prime number divides product of k integers, then it divides at least one of them. Use the induction to prove this. And finally, we come to the proof of uniqueness of prime factorization. So this requires first writing down the two possible prime factorizations and proving they are actually equal up to rearrangement and relabeling. Okay. The main idea is this reducing step where we have two prime factorizations are equal, then the first prime P1 divides the right side. So it is dividing at least one of these Qj. And if that happens, that prime PQj must be the same as P1 since they are all prime numbers. So up to rearranging, we can send the Qj to Q1 and replace it with the Qj. Then, since now P1 equals Q1, we can remove the P1 and Q1 from our listing. of the prime factors. So we have the double star equation here. P2 through Pk equals Q2 through Ql. So if K and L are not the same to begin with, then this reducing step will eliminate one side completely, and the other side, some prime factors remain. And this cannot happen because product of any number of prime numbers cannot equal 1. So we must have K equals L. The number of primes in the listings should be equal. And then the elimination step will eliminate one prime at a time. So that at the final step of elimination, we will have 1 equals 1. So both sides are completely eliminated. This shows that up to rearranging, Pi must be Qi for all I. So the first two listings should be indeed identical up to rearranging the primes. Okay, so we have a proof of uniqueness of prime factorization. Okay, so next one is, as we have the uniqueness of prime factorization, we can use our prime factorization with distinct primes P1 through Pk. Okay, so we want that Pi's are distinct primes so that the repeated primes can be collected together. So if we have P1s together, and the number of P1s in the prime factorization is A1. And so that goes all the way up to Pk to Ak. So this exponent Ai is how many times the prime Pi is repeated in the prime factorization. Okay. So if a number m, integer m, is greater than 1, if it is a divisor of n, then the integer m can be written also with the same set of prime numbers, P1 through Pk, as of the n, with exponents B1 through Bk, with at least one of the Bi is non-zero. The proof of that is any prime q dividing m must also divide n. And since the divisibility is transitive, so we can conclude the q also divides the integer n. That means in the prime factorization of n is this. In the prime factorization of n, the prime factors possible are P1 through Pk. So this prime q must be one of those. Therefore, it follows that the m has a factorization using this listing of primes only. So let the B1 through Bk be how many times they are repeated. P1 repeated B1 times, all the way up to the prime Pk repeated Bk times. Okay. Moreover, each Bi cannot exceed Ai, since m must divide n. Okay. That means the number of repetition in the divisor cannot exceed the original number. So B1 cannot exceed A1. Bk cannot exceed Ak. And since m is greater than 1, at least one of the Bi is non-zero. Okay. But it doesn't hurt us to include the 1. Okay, note that. If n has this prime factorization with distinct prime numbers, P1 through Pk, then for any, so without a restriction of greater than 1, for any m dividing n, we have m is p1 through b1 all the way up to pk to the power of bk, with the bi's are greater than or equal to 0. Okay. So then the two extreme cases are all bi equal to ai. Then we must have m equals n. By the uniqueness of prime factorization, if the exponents are all the same, then we must have the same number. Another extreme case is the smallest extreme. All bi is 0. Then in case all the bi's are 0, then the m is necessarily 1. Okay. 0th power is 1. So then any proper divisor of n will be in between 1 and n. Okay. Proper divisors of n are the m dividing n and 1 less than n less than n. That's called a proper divisor. So does the prime number have any proper divisor?
No.
No. Having no proper divisors is exactly the definition of prime numbers. Okay. Next, theorem 819. So now we prove the set of prime numbers is infinite set. Okay. This is infinite set, and the proof is given by Euclid. This is a very, very famous proof. And if you have a mathematics major, or if you're planning to study more about the mathematics, then you must remember the proof. The proof idea is the proof by contradiction. So what is the proof by contradiction? The main structure of it is you first assume the negation of the conclusion and find the contradiction. So if you assume the negation of conclusion, you have a contradiction. So that way, it means that the negation of conclusion must be incorrect. That way, we're proving that the conclusion must be true, right? That's the main structure of proof by contradiction. So in this statement, set of primes is infinite. That's the conclusion. So we negate the conclusion, then assume to the contrary that by contradiction to the contrary that there are only finitely many primes. Okay, only finitely many primes. The finitely many means what? well, it's not infinite, so there has to be a listing of all prime numbers which ends at some point. Okay. So say P1 through PK. P1 through PK, those are our all possible prime numbers. And now consider an integer capital N, which is product of all primes plus 1. Okay? That is well defined since we're assuming the finiteness of the set of primes. Okay. And this is an integer that's greater than 1 because each prime number is greater than or equal to 2. That number capital N is always greater than 1. So any integer greater than 1 admits a prime factorization. Okay.
Can you explain that part? Like, I don't,
This part?
what you just said.
So this capital N, it is greater than 1. Since any primes in here is greater than or equal to 2, so the capital N is greater than 1. Any integer greater than 1, it had a prime factorization.
Okay.
So consider.
And sorry, I have a question also. What is the point to add 1 to the positive integer n to n? Yeah.
So we will see the effect of the plus 1 later if we follow along the proof.
Oh, okay.
Okay. So consider any prime factor of n, prime factor q of n. Since n admits prime factorization, it must have a prime factor. Okay. And say that is a q, a prime factor of capital N. And by assumption, and what is our assumption?
They're finite.
Finitely many primes, P1 through Pk only. And Q is a prime number. So Q must be one of those. Q must be Pi for some I in 1 through K. Okay?
Yeah.
So after re-indexing, let this Pi be just P1. So you replace Pi with the P1, interchange it. Okay, so we can say Q equals P1. That doesn't hurt us. So with this re-indexing, we can write the capital N as Q times P2 through Pk and plus 1. Because Q was P1 now. Q was P1. And remember, Q was a prime number, so it's greater than 1. Okay? So we get a remainder of 1 when we divide capital N by Q. N equals Q times integer plus 1. So we get a remainder 1 after dividing N by Q. Therefore, the Q cannot divide the capital N.
You get remainder of 1 because of the plus 1, and
Yes.
they're all 1.
Thus, Q cannot divide N. Okay, since you get a remainder 1, Q cannot divide N. However, the Q was given to be a divisor of n. Q must be a divisor, prime factor of n, right?
Yeah.
So we have two opposing statements. Q cannot divide n, and Q is a divisor of n, right? So this is a contradiction.
And how we get the Q divisor of n?
Q is a divisor of n in here. So we started off with consider any prime factor Q of n. So Q was given to be a divisor of n. Okay?
Okay, thank you.
So we got the contradiction. So getting a contradiction means the original conclusion must be correct. So this conclusion must be correct. Okay? Assuming finiteness, we get a contradiction. So the set of primes must be infinite. Okay?
Is it hard to find more primes like as you keep going? That's what I've heard. That it's difficult to find prime numbers as you keep going down the line of integration.
Yes, yes. So the research along this line concludes that let pi x be the counting function of prime number up to x, then pi x times log x. This log x is natural logarithm. After the limit x goes to infinity, this is 1. And that means the number of primes up to x is approximately x over natural logarithm of x. So as x keeps going on, the density of the primes is approximately 1 over log x. So it becomes sparse and sparse as you go along. If the numbers are larger, it is harder to find the primes. Okay? This statement is called the prime number theorem. Okay?
So for our assumption, if we don't have one, we will not have the contradiction, yes? For the previous one?
Mm-hmm.
Yeah.
So
if we don't have the plus one, we will not have this contradiction. It will agree, yes?
That is right.
Yeah, okay. So we'll put this one to have the contradiction in the final proof.
Yes.
Yes? Okay,
Yes.
thank you.
Okay, so next example is a proof of irrationality of the square root of 2. So if you're majoring mathematics, this is also one of the very typical easy proof that you need to remember how to do. Square root of 2 is not a rational number. And if you have been in my math 320 class, then you have seen this proof. So this structure of the proof is again the proof by contradiction. So let's assume to the contrary that square root of 2 is rational. So being a rational number, it means we are able to write down fraction of integers. So we may write for some integers such that root 2 is a over b, GCD is 1, okay? And we must have also non-zero b, b is non-zero. So multiplying b both sides, we obtain b square root of 2 equals a.
We
Okay.
have GCD of A and B equal 1 because they are relative prime.
Yes.
How we know?
So if it is not, then we can cancel the common factors. So think about 15 over 10, right? GCD is not 1.
Yeah.
GCD is 5. We can cancel the 5 and make it into the reduced fraction. Okay. Well, when you made it 3 over 2, they don't have any common factor. So if we have common factor, we can keep canceling out until you have no more common factors in the numerator and the denominator. That's why we are okay to assume that GCD of A and B, GCD of the numerator and the denominator equals 1.
Because we don't have, we can't factor in more than square root of 2. Yes.
That's right. We cannot have any more factor.
Thank you.
So we multiply b both sides to have b root 2 equals a. And we square the sides. So left side square is b squared times 2. And the right side square is a squared. So we obtain this identity. The left side is 2 times an integer, right? That means the left side has 2 as a factor. 2 is a prime number and 2 has a factor. So the prime factorization of the left side should contain the prime number 2. So that's what's happening on the left side. It has a prime factorization with a list of the primes include the 2, but that equals the a squared, which means that the number 2 must divide a squared.
Why?
So a squared is 2 times another integer.
Oh, okay.
So 2 divides a squared. And look at this here. This gives 2 divides a. How is this possible? We know that 2 divides a squared, but does it mean 2 divides a?
The product A times A, so 2 must divide one of A. So A and A is 30.
Yes, that's true. A squared is a times a, so 2 must divide a. So we are able to write down a as a 2 times integer. 2 divides a, so a equals 2 times the integer for some k. And this time, from this left side is 2b squared, the right side is square root of the 2k. And square root of the 2k is 4k squared. And you cancel out the 2, we obtain b squared equals 2k squared.
Oh, you substitute for A 2K, yeah? Okay.
That's right, yes. So by the same reasoning as before, b squared is 2 times an integer. So 2 divides b square, right?
Yeah.
Yeah. And that gives us 2 divides b. So it should be b. It's a typo in my notes. Two divides b times b, so 2 must divide b. And that contradicts GCD of AB equals 1. How can we know this is a contradiction? Go back to 2 divides A.
Because 2 divides
Also,
2 divides b.
Yes. 2
But
divides A.
if it divide one all of them, it can be GCD of A and B equal 1.
So that's right. So B, A and B both have 2 as a prime factor. So that contradicts the assumption of GCD is 1. Okay?
No, my question if is 2 divide only one of them, like divide the A only.
Mhm.
So the GCD, it can be 1 between A and B?
GCD in case if 2 divides A and 2 doesn't divide B,
Yeah.
the GCD may be 3, for example, or 5.
Or 1 if we can't factor anymore. Yeah.
Mhm.
Okay. Thank you.
So we got the contradiction. Therefore, the square root 2 must be irrational number. This is not represented as a rational number. We just found a contradiction. The square root of 2 is not a rational number. Okay? All right? So, exercise for you is prove that square root of 10 is irrational. Okay? So you modify this argument to prove that square root of 10 is irrational. All right? So these were H4, these were in the Math 320. But this time, some of them might be included in the homework 1. Right, so this exercise is given 2 integers A and B with at least one of them is non-zero. And write down H as the A divided by the GCD of A and B. K equals B divided by GCD of A and B. And then you can show that the GCD of H and K equals 1. So what this basically does is H and K is dividing by the common factors of A and B. So all the common factors are divided since you divided by GCD. So there should be no more common factor to H and K. So it's quite clear that GCD must be 1. Right? Next exercise. If A and B are non-zero integers with GCD equals 1, so no common factor between A and B, and C is an arbitrary integer, and then A divides C, B divides C together implies A times B divides C. And give an example to show that this result is false if GCD of AB is not 1. So AB doesn't have any common factor, and assuming A divides C and B divides C, it is also true that A times B divides C. Okay.
So we want to show AB the divide C,
Yes.
and they give example for this.
If the GCD
There is
is not 1, then give the example that this is
It's
false.
false.
Yeah.
Okay. Thank
So hint to this problem is using the Badge's theorem. The GCD of AB is 1. Then there are integers x and y such that ax plus by equals 1. And multiply c both sides. Then we obtain c times by equals c times 1 minus ax. The cax is moved to the right side. Now use the facts a divides c and b divides c. So how can we use this?
Can we see C equal AK for some K and Z? Or AX?
So ax is
Can we
divisible
see
by a.
Can we see C equal AX for X integer and B equal C equal BY?
So we need to use the c equals ak1 and c equals bk2. Okay. Then what can we conclude here?
AK1 equal BK2.
Yes, ak1 equals bk2. However, more helpful way towards solving this problem would be, since we're proving that c is divisible by a times b, right? To prove that c is divisible by a times b, the cax, what happens to cax? Cax is substituting this a, b, k2, and x. And cby substituting a k1, a, b, k1, y. So both cax, cby are divisible by a times b. They have the ab here, ab here. So the both parts, cax and cby, both parts composing the c are divisible by ab. Therefore, c is divisible by ab. Okay? So that's the idea of the proof. But another idea is to use the fundamental theorem of arithmetic. This is the existence and uniqueness of prime factorization, showing that the list of prime factors do not overlap. A and B are also to be relatively prime, therefore, prime factors do not overlap. Okay. So in such case, assuming that C is divisible by A, the C must include all the prime factor listings of A. Also, it also includes the prime factor listings of B. And the listings of A and B, they do not overlap because of assumption of the relatively prime. So all of these listings should be there, should exist in the listing of prime factors of C. Therefore, C must be divisible by A times B. Okay. So far,
To give example, we give number, a specific number. Yeah? For example, A equal
that's right.
3,
Yeah.
B 4, C 5.
What numbers do you say?
Like a 3, 4, 5 for A and B and C. So A, B, it will be 12. Doesn't, so 5 doesn't divide 12.
You might want to give the example satisfying A and B GCD is not 1.
Yeah, 3 and 4. 3 and 4. Oh, not 1?
3 and 4, 1. Yeah.
Oh, okay.
You might want to give a 2
And 4.
is 4. Then the GCD is not 1.
Okay.
Yeah.
We have to give also C a number, yes, like 5 or any number.
But this is not a good example indeed. Because A divides C, B divides C together. A times B. A times B is 8. So we might find an example. We might find an example with A equals 2 and B equals 4.
Yeah, like it gives C like 5 or
No,
3.
C cannot be 5 since 2 divides 5 it's not possible.
Oh, okay.
So 4 divides 5 is not possible. So the number you might want to give is C equals 4. So then A divides C is true. B divides C also is true. But A times B, which is 8, cannot divide C. So that is the desired example.
Yeah, false. Yeah. Thank you.
Okay. So far we did the infinitude of prime numbers also. The expression of the prime factorization according to the multiplicity. Okay. So the exponents represent how many times each prime number is repeated. And proof of the infinitude of prime. And the proof of square root of 2 is irrational number. Right? Okay. Now let's cover some topics that's in the 360 textbook. There are some overlaps with chapter 1 and the previous ones. So from starting from notes will be covered in the quizzes or the exams and the homework. Okay. But of course, you won't need these previous materials. Those are indeed in the Math 320. Okay, so let's begin with linear Diophantine equations.
Professor,
Linear, yes.
is that posted on Canvas already, or is that not yet posted?
Let me see. In this note, right?
Yeah, this portion of the notes.
Oh, it's not yet. I'll do it right now. Sorry.
Okay, awesome. Thank you.
So our first quiz, it will cover from this one, linear, yes? Not from the previous section, yes?
That is right. Yes.
Thank you.
Okay, I just downloaded on Canvas. This is the file Math 360 topic 1-first. We start with the linear Diophantine equations. The linear Diophantine equation is the equation of this form, ax plus by equals c, where the integers a, b are given, also c is given. Okay? And a and b are assumed to be all non-zero, and c is any arbitrary integer. So we are concerned about solubility of this equation in the integers x and y. Look for the solutions x and y in integers. Okay. The linear Diophantine equation has an existence criterion. Such equation ax plus by equals c, it has solutions in the integers. So g squared means x is integer, y is also integer. If and only if the GCD of A and B divides C. Okay, so forward implication. If x and y both are integers satisfying this equation, then obviously GCD of A and B must divide A, it must also divide B. Therefore, we must have GCD of A and B dividing the ax plus by equals C. So GCD of A and B must divide C.
X and Y here in Z square or R square?
Z squared.
Does it make difference if it's R square?
Yes. If it is R squared, that means x and y are real numbers,
Okay. So here just the integer.
just the integers. So
Okay.
if you look at the xy plane, the R squared means any point in the plane. But the Z squared means only the lattice points. Only the components are integers. All the points over on the lattice. Okay.
I ask this because first time to see Z square. Thank you.
Yes. So this forward implication is just proved. Okay. But for the backward implication, we will actually give a solution procedure and how to explicitly find out the solutions in x, y in integers. So in this section, we see how to find solutions. This will also provide the proof of the backward implication of the existence criterion. Okay. So assume that the GCD of AB divides C. Now we are trying to find the integer solution to this Diophantine equation. And let C0 define the C0 number, C over the GCD of A and B. Because of this assumption, because of this, this C over GCD must be an integer. So from this equation, we may actually divide all the terms, all the coefficients, by the GCD of A and B. All right. Here, some part is missing. Definition of A0 and B0. Definition of A0 is A over GCD of A and B. Definition of B0 is B over GCD of A and B. Note that this divided the common factors of A and B completely. So A0 and B0 should not have any common factors now. So GCD of A0, B0 is 1. And once you divided the original Diophantine equation by the GCD of A and B, then we obtain A0x plus B0y equals to C0. Okay. By Badge's theorem, there are x0 prime, y0 prime integers for the relatively prime pair A0, B0. We must have integers x0 prime, y0 prime such that A0 times it plus B0 times it equals 1. Okay. Then we have A0 x0 plus B0 y0 equals C0 with the choice of C0 x0 prime and C0 y0 prime as x0 and y0. So going from here to here is multiply C0 both sides. Okay, and write down the x0 as C0 x0 prime and C0 y0 prime for y0. Okay, so we got the existence of the integer as xy. In such case, GCDAB dividing C. And now, to represent all solutions to this Diophantine equation, let x and y satisfy the star. The star is this star. A0x plus B0y equals C0 equation. So let's call that reduced equation. All right. If x1, y satisfy the star, then the right side is C0. So A0x plus B0y supposed to be equals C0. And with our x0, y0 choices, A0, x0 plus B0, y0 equals C0, 2. All right. So both equal C0 and they are obviously equal. So now, factor out the A0 part only. So collect the terms that having the A0. Similarly, collect the terms having the B0 and write them on the other side. Then we obtain this equation. And think about now, A0 and B0 don't have any common factors. Therefore, this B0, it must divide this. And this A0, it must divide this. Okay, so using this divisibility, B0 divide x minus x0, we are able to put x minus x0 as b0 times t. Okay, so x minus x0 is b0 times t for some integer t. Then a0 b0 t equals b0 y0 minus y. This is because we are putting the b0 t in place of x minus x0. Then we can see b0s are in common, so we cancel them out. So that a0 t equals y0 minus y. The purpose of solving this is solving for x and y. So isolate the x and isolate the y. Isolate the x from this, so that's x equals x0 plus b0 t. And isolate the y from here to have y0 minus a0 t. T is integer.
Professor,
Yes?
how'd you get that b0 divides x minus x0?
B0 divides x minus x0 from this identity.
Oh, okay.
Yeah. So B0 exists on the right side, but for the B0 as a factor of this integer, B0 and A0 have relatively prime, so they don't have any common factor. So consider the prime factorization. So everything appears in the B0 should appear in the x minus x0.
Oh, okay. Thank you.
So we obtain this parametric form of the solutions. And for the integer parameter t, x can be written as x0 plus b0 t, y0 minus a0 t. Y can be expressed as y0 minus a0 t. Okay. So x0, y0, these ones may be regarded as an initial solution. Okay. This expression may be regarded as general solution. Okay. Or particular solution and general solution. That's the terminology that we used in the differential equations. Okay. So the third step is how to find the particular solutions. Okay. So in this, back to this step, it requires us finding x0 prime, y0 prime. So we go back to there. How to find the x0 prime, y0 prime from the Euclidean algorithm. So here we use the extended Euclidean algorithm, not just the a equals bq plus r, with r is a remainder. The extended Euclidean algorithm tells us that not only this, but also the GCD of A and the divisor B, okay, A and the B equals GCD of B and the remainder. All right. So look at this one. If A0 is 134, B0 is 121, then dividing 134 by 121 with the remainder 13. So this way of writing is 121 multiplied by 1. So write down the result of the multiplication and write down the result of the subtraction. So that this is 13 is the remainder. On the next round, copy down 121. And what we obtain by now is the original GCD of 134, 121 should be equal to the GCD of 13 and 121, right? So
Sorry,
at
can
each
you repeat
round,
that one more time?
yes. GCD of 134, 121 equals GCD of 13 and 121 because of this. So here, A and B and R. GCD of A and B equals GCD of B and R. Okay. The next step, in the next round, now we use this number for the dividing. Okay. If we multiply by 9, then the result is 117. Then after the subtraction, the result is 4. And copy down the 13. So that's the GCD of 13.
Can you repeat
and
that one more time,
121.
Professor?
Which part?
The 121 where you get to the 117.
Oh, it is a division. 121, try dividing 121 by 13. The quotient is 9.
Okay, yeah, I
Yeah.
got it.
So 8 is too small, 10 is too large, 9 is the right one. So 117. Then you subtract the 117 from 121. The result is 4.
Is this kind of like mod?
Yeah. So then copy down the 13. And it means by the Euclidean algorithm, it is 13 and 121 GCD equals to the 13 and 4 GCD. Okay. So we're at the third round of 13 and 4. So divide 13 by 4 with the quotient is 3. The remainder is 1. 4 times 3 is 12. After subtraction, it is 1.
So we stop when we get the remainder one.
So it means that the GCD of the 134 and 121 is same as GCD of 1 and 4. So at each beginning of the round, first round, second round, third round, and fourth round. At each beginning of the rounds, their GCD is always the same. But now at the fourth round, it's quite easy to see what the GCD is. What is it? GCD of 1 and 4?
Just one.
That's 1. Yes. So GCD of 13 and 4 is 1. Yep.
And at this step, we stop. When we got the GCD one, we stop our.
Yes.
Okay.
But to find the x0 prime, y0 prime, that's the integer linear combination equals to the one with the relatively prime integers a0 and b0. Here's how you can do. So you trace by placing a0 and b0 first, and trace what number you have at each round. So here 13 is obtained by a0 minus b0 times 1. Okay. So that's what the 13 is. Then go to the number 4 and trace how it is obtained. The 4 is now 121 minus 117. But 121 was B0. 117 is 9 times 13. 13 was A0 minus B0. thereby obtaining minus 9a0 plus 10b0. So at this point, we got the linear combination of a0 and b0 to make the 4. Okay. Then the next is now finally the 1. Okay. Next is 1. And trace how it is obtained. It is obtained by 13 minus 12. And 13 minus 12 is 13 from a0 minus b0. That was the 13. And the 13 minus 4 times 3 makes the 1. And we obtain the 4 equals this. So this is 4. So 13 minus 3 times 4. That's how we made the 1. And at this point, we are able to collect the like terms together. a0 like terms is 1 times a0 minus 3 minus 9 a0. So 1 plus 27, which is 28. Okay. The b0 like terms, minus 1 and minus 30. So minus 31. Minus 31 b0. Right. So what did we obtain now? Integer linear combination of a0 and b0 that equals 1. All right. So x0 prime is 28 and y0 prime is negative 31. Okay. So for example, find all solutions to the 4x plus 6y equals 10. The first step is divide both sides by GCD. GCD of 4 and 6 is obviously 2. 4 is 2 times 2. And 6 is 2 times 3, so GCD is 2. So divide by that, we obtain 2x plus 3y equals 5. The next step is find the x0, y0 either by inspection. For the small numbers, it's possible to find them by just inspection. You can see the 1 and 1 works for this. So that is the lucky case. If we can find it by inspection, then we just use that. And we write down 2x plus 3y equals 2 times 1 plus 3 times 1 with the x0 and y0. So then 2 times x minus 1 is 3 times 1 minus y. With x minus 1 must be, this x minus 1 must be divisible by 3. This 1 minus y must be divisible by 2. So if we substitute x minus 1, 3t, then automatically 1 minus y is 2t. Then solve for x and y. X equals 1 plus 3t, y equals 1 minus 2t, with the parameter t in integers. Okay. So by inspection, we obtain 1, 1 is a solution to the original Diophantine equation, 4x plus 6y equals 10. And we are able to write the general solutions with this form. So anything of this form with the t integer is a solution to the equation. So for example, t equals 1. This is t equals 0 case. For t equals 1, then it's 4 and negative 1. You can see easily 4 and negative 1 solution to this. 4, negative 1. That makes the 10. 4 and negative 1. 8 minus 3. Another example, when t equals negative 1, then negative 2 and 3. That's another solution. And all other solutions can be written this way. T equals 2 t equals -2, and so on. So we indeed have infinitely many solutions to the original Diophantine equation.
In the
So
quiz,
yes,
in the quiz, you want a general solution or you want both, for example?
just this one should be fine. Just the parametric form should be fine. You don't need to write all the solution this way, because this is already listing of all the solutions.
Thank you.
All right. The next example, 134 and 121. We have been using 134, 121 already. Okay, for this one, finding the solution by inspection is very hard because of the large numbers. So we apply the Euclidean division algorithm, the extended one, to find the x0 prime and y0 prime. In the earlier table here, we found x0 prime, y0 prime satisfies 1 equals 28 at a0 minus 31 b0. So with this, we want to first look at the initial solutions with 23 times 28 as x0. 23 times -31 as y0. Okay. With that, 134 times x minus x0 equals 121 times y0 minus y. So that since they are relatively prime, x minus x0 is 121t. y0 minus y is consequently 134t. Okay. So x equals x0 plus 121t, and y is y0 minus 134t. And now compute the x0 and y0. x0 was 23x0 prime. 23 times 28, 644. And y0 is 23y0 prime. 23 times minus 31, minus 713. So the general solution is x equals 644 plus 121t. Y equals minus 713 minus 134t with a parameter t in integers.
So if we don't have the previous example, we have to solve for x prime and y prime.
Yes, that's right. Since we had this calculation already, we are
already, yeah.
using,
But if it's like a regular problem, we have to go with this first step. Yes. Thank you.
Yes, yes. Okay. All right, so that's it for today.